Welcome to Context. This is Brad Harris. Today, we're discussing the iconic book by Thomas Kuhn, The Structure of Scientific Revolutions. This episode is supported by you, those of you who value my work enough to reciprocate through Patreon or PayPal. I think there are some problems with how history is typically taught in academia, and I'm trying to address some of that through this venture. I go into more detail about this on my Patreon page, so if you're interested, you can learn more there. In any case, even in the best scenario, most university professors can only reach small, arbitrary numbers of privileged students and colleagues. But through this podcast, I can connect with you, no matter who you are or where you are. So thank you to those of you who support me. You are making this possible. And if you haven't taken that step yet, but you'd like to support this podcast, go to bradharris.com to get on board. And now, for The Structure of Scientific Revolutions by Thomas Kuhn. The Structure of Scientific Revolutions was first published in 1962, but it attracted so much attention and proved so disruptive that second, third, and fourth editions followed. It rapidly achieved the status of a classic in the history of science, and ultimately became one of the most frequently cited books of the 20th century. Among young academics in particular, referencing Kuhn became a badge of intellectual enlightenment from the 1970s onward, a signal that you had transcended the vulgar historical interpretations of the masses and become a bona fide professional thinker who understood just how problematic terms like scientific progress and truth really were. Through the 1980s, it became fashionable among intellectuals to rally Kuhnian theory in denying not only the existence of truth, but its virtuousness as well. After the 1990s, by which time an entire generation of scholars in the humanities and social sciences had come of age, percolating in Kuhn's opaque stew of ideas, graduate students studying under them who dared to interpret science as the pursuit of objective knowledge were rebuked for outdated thinking. Who was Thomas Kuhn, and how could his book have caused such an intellectual upheaval? First, it's important to acknowledge that The Structure of Scientific Revolutions actually was a very insightful book, which greatly enhanced our understanding of the history of science. It deserved plenty of attention and praise. And Thomas Kuhn was a creative, multidisciplinary thinker. The man was a physicist turned philosopher of science who obtained a PhD in physics from Harvard in 1949. He died in 1996 at the age of 73. Now, on the way toward getting his PhD, Kuhn helped teach an undergraduate course on the physical sciences designed for non-science majors, and in the process, he was exposed to the field of the history of science for the first time in his life. In his own words, quote, "That exposure to out-of-date scientific theory and practice radically undermined some of my basic conceptions about the nature of science. The result was a drastic shift in my career plans, from physics to the history of science." End quote. Thereafter, Kuhn abandoned physics and dove deep into social science, focusing on psychology, linguistics, and philosophy. He was fascinated by how social scientists problematized, which is to say, questioned, interrogated, and complicated the nature of scientific investigation. What were scientists really up to, Kuhn's new cohort pondered in excruciating detail. From this academic foray, Kuhn grew convinced that there was something deeply wrong with people's assumptions about how science works. Traditionally, according to Kuhn, we are taught that science simply represents a collection of facts, concepts, laws, or theories that are accumulated like the bricks of a building in, quote, a piecemeal process to the ever-growing stockpile that constitutes scientific technique and knowledge, end quote. In this sense, Kuhn's portrayal of the traditional history of science is one of linear progress, a smooth accretion of objective knowledge about how the world works, a heroic struggle against ignorance through which lone geniuses and lab technicians alike push humanity ever onward in a steady march of scientific progress. Yet, Kuhn became convinced that this image of science, quote, is no more likely to fit the enterprise than an image of national culture drawn from a tourist brochure, end quote. What was actually occurring through the history of science, he intended to show, was something quite different. There are phases within the history of science, Kuhn admits, when investigators may appear to make linear progress, accumulating insight on a particular question about the world piece by piece, refining their theory by testing ever more precise hypotheses. This is what Kuhn calls normal science, and it functions within what he calls a paradigm. However, any particular paradigm of normal science is only a phase within a larger historical cycle, a cycle whose structure is characterized not by continuity of progress, but by disruption, by revolution, by paradigm shifts. When most of us think of scientific revolution, we think of the scientific revolution of the 1600s, when the basic methods of modern science were established in the first place. However, for Kuhn, that was only the most dramatic example of science's cycle of disruption, of science's paradigm shifts, to use Kuhn's language. In Kuhn's opinion, the entire history of science was little more than an endless cycle of revolutions, and he laid out the structure of that historical cycle as follows. First, you start with a phase of normal science operating within an established paradigm in which investigators share assumptions about how the world works. They agree on what problems are appropriate to ask and what investigative tools are appropriate to use. Working within that paradigm, scientists are not actually trying to make discoveries. They're not pursuing novel insight at all. Instead, he argues, they're merely trying to confirm the paradigm itself. Everything they do is structured to confirm their assumptions about how the world works, and whenever they actually do encounter something unexpected, a strange piece of data, say, or a novel experimental result, they tend to ignore it since it doesn't fit with the established paradigm. Kuhn equates this activity with puzzle solving, in a very literal sense. Imagine yourself trying to solve a puzzle. You have a bunch of pieces jumbled together, but you also have the final image of the puzzle on the cover of the box those pieces came in. So you know what you're trying to do. You're trying to put those puzzle pieces together to match that image. You're not trying to discover new images that you can create with the pieces you have. That would be missing the whole point. So when you encounter a puzzle piece that doesn't seem to fit the image you think you're supposed to reconstruct, and you don't know what to do with it, you simply put it aside, right? You ignore it, at least for the time being. Puzzle solving is what scientists are up to most of the time, according to Kuhn, and all of their assumptions about what they're supposed to be trying to do, how they're supposed to put all the pieces of their assumptions of how the world works together, define their scientific paradigm. Their pieces of the puzzle, of course, are mathematical equations, experimental data, and investigative observations, and their image on the front of the box is the paradigm itself, the worldview they share, the expectations they hold about what their equations and experiments and observations should reveal. Puzzle solving usually occupies generations worth of scientific labor. As Kuhn writes, that is normal science, after all. However, the longer that scientific puzzle solving goes on, the more pieces accumulate that scientists can't get to fit the paradigm. He calls these anomalies, and the more of them that pile up, the more unstable the paradigm becomes. Eventually, a crisis erupts within the scientific community. What if the paradigm itself is wrong? This would be akin to you working on a puzzle that eventually proved so unsolvable that you came to suspect that the puzzle manufacturer printed the wrong image on the front of the box. At this point in the structure of the historical cycle of science, the crisis of too many anomalies leads to a scientific revolution. A paradigm shift occurs, and scientists suddenly find themselves working out the puzzles of an entirely new worldview with an entirely new set of assumptions about what the right questions are and how to go about answering them. A useful example of paradigm shift that Kuhn highlighted comes, not surprisingly, from the scientific revolution itself, with the emergence of Copernican astronomy in 1543. Up to that time, Western civilization's understanding of astronomy was based on the Ptolemaic system, featuring the Earth at the center of the known universe, which had been developed some 1,500 years earlier, and for a while, quote, it had been admirably successful in predicting the changing positions of both stars and planets. No other ancient system had performed so well, and for the planets, Ptolemy's predictions were as good as Copernicus's. But to be admirably successful is never, for a scientific theory, to be completely successful. Predictions made with Ptolemy's system never quite conformed with the best available observations. End quote. For centuries, normal science and astronomy, Kuhn argued, was focused on trying to solve the puzzles represented by the discrepancy between Ptolemy's predictions and the actual positions of stars and planets at any given time. Quote, given a particular discrepancy, astronomers were invariably able to eliminate it by making some particular adjustment in Ptolemy's system. But as time went on, a man looking at the net result of the normal research effort of many astronomers could observe that astronomy's complexity was increasing far more rapidly than its accuracy, and that a discrepancy corrected in one place was likely to show up in another. In the 16th century, Copernicus's co-worker, Domenico da Novara, held that no system so cumbersome and inaccurate as the Ptolemaic had become could possibly be true of nature. An increasing number of Europe's best astronomers were recognizing that the astronomical paradigm was failing in application to its own traditional problems. That recognition was a prerequisite to Copernicus's rejection of the Ptolemaic paradigm and his search for a new one. End quote. A key part of Kuhn's analysis comes several chapters later when he asserts that Copernicus's alternative astronomical theory, featuring the sun at the center of the known universe, quote, was neither simpler nor more accurate than Ptolemy's system. Available observational tests provided no basis for a choice between them. Under those circumstances, one of the factors that led astronomers to Copernicus was the recognized crisis that had been responsible for innovation in the first place. Ptolemaic astronomy had failed to solve its problems. The time had come to give a competitor a chance. End quote. In other words, Kuhn argued that it wasn't the case that Copernicus succeeded in persuading people that his theory was any truer. Rather, it was that Ptolemaic astronomers had grown so frustrated by all the unsolvable puzzles of their own worldview that they decided they might as well give Copernicus's puzzle a try. An important thing to realize about Kuhn's notion of paradigms and paradigm shifts is that he went to great lengths trying to explain how the ideas and assumptions of one paradigm were incommensurable with those of another. Once a scientific revolution occurs, he argued, scientists working within the new paradigm hold entirely different assumptions about how the world works, about what problems are even real and solvable, and even about the very definition of what is and what is not scientific. He provided a couple of examples. Quote, those who scoffed at Einstein's general theory of relativity because space could not be curved, it was not that sort of thing, were not simply wrong or mistaken, nor were the mathematicians, physicists, and philosophers who tried to develop a Euclidean version of Einstein's theory. What had previously been meant by space was necessarily flat, homogeneous, isotropic, and unaffected by the presence of matter. If it had not been, Newtonian physics would not have worked. To make the transition to Einstein's universe, the whole conceptual web, whose strands are space, time, matter, force, and so on, had to be shifted and laid down again on nature whole. Consider for another example the men who called Copernicus mad because he proclaimed that the earth moved. They were not either just wrong or quite wrong. Part of what they meant by earth was fixed position. Their earth, at least, could not be moved. Correspondingly, Copernicus's innovation was not simply to move the earth. Rather, it was a whole new way of regarding the problems of physics and astronomy, one that necessarily changed the meaning of both earth and motion." End quote. Kuhn's insistence here on the incommensurability between paradigms seemed to have radical implications. As the historian of science Ian Hacking pointed out, many people interpreted this to mean that new scientific theories were not developed to replace old ones because they were truer, but merely because they reflected a change in scientists' worldview that better fitted whatever puzzles they were trying to solve. And that idea, in turn, led many of Kuhn's readers to conclude that scientific progress doesn't really exist at all. Kuhn himself, toward the end of his book, only added fuel to this nihilist fire by concluding, quote, "We may have to relinquish the notion, explicit or implicit, that changes of paradigm carry scientists and those who learn from them closer and closer to the truth." End quote. So, as far as Kuhn was concerned, what was science, if not a process for making progress toward truth? Well, from his perspective, science was better understood more as, quote, "a process of evolution from primitive beginnings, a process whose successive stages are characterized by an increasingly detailed and refined understanding of nature, but not a process of evolution toward anything." End quote. This was a subtle distinction that many of Kuhn's readers missed. He admitted repeatedly that the process of science does refine our understanding of nature, just not in the way we traditionally supposed. Quote, "We are all deeply accustomed to seeing science as the one enterprise that draws constantly nearer to some goal set by nature in advance. But need there be any such goal? Can we not account for both science's existence and its success in terms of evolution from the community's state of knowledge at any given time?" End quote. Indeed, evolution becomes the functional analogy toward the end of the book. Just like Darwin's theory of natural selection explains how biological complexity evolves in the absence of any kind of purpose or end goal, Kuhn leaves us with an image of science that evolves increasingly sophisticated concepts of the world in the absence of any real direction other than that which enables scientists to solve particular sets of puzzles. As I said at the opening of this episode, this interpretation certainly did offer a valuable new perspective on the history of science. The problem was the subtlety of Kuhn's argument, combined with his vague and often impenetrable writing style, unleashed a groundswell of misguided interpretations of his work, igniting a cultural movement within academia energized around the confused conviction that objective truth was an illusion and that scientific progress was just a conceit of Western civilization. These ideas became pillars of postmodernism, and no one was more frustrated by the folly of their development than Thomas Kuhn himself. To cite the historian of science Ian Hacking again, who wrote the introduction to the 50-year anniversary edition of The Structure of Scientific Revolutions in 2012, published by the University of Chicago Press, Kuhn's argument was, unfortunately, quote, "abused by the wave of skeptical intellectuals who called the very idea of truth into question." Kuhn had no such intention. He was a fact lover and a truth seeker. End quote. As early as 1970, Thomas Kuhn had started to lament publicly that he'd lost control of his narrative. One of the most probable reasons why so many people may have misinterpreted his message derived from his opaque use of metaphor. He constantly wrote phrases like, quote, "After Copernicus, astronomers worked in a different world," end quote, and, quote, "After discovering oxygen, Lavoisier lived in a different world," end quote. Careful readers could parse the intended meaning, that scientists simply gain new perspective after discovery. But after hundreds of pages of such writing, many readers emerged with a peculiar sense that the state of the world itself is contingent upon however humanity happens to interpret it. This converted scientific objectivity into scientific relativism. The world is whatever we make of it. Facts are socially constructed. As Ian Hacking surmised, quote, Kuhn made plain that he himself detested that development of his work, end quote. In the aftermath of the intellectual upheaval he triggered, Kuhn emphasized passages of his book in speeches and interviews that he hoped would counteract the truth deniers, exclaiming, quote, "After a scientific revolution, many old measurements and manipulations become irrelevant and are replaced by others instead, but changes of this sort are never total. Whatever he may then see, the scientist after a revolution is still looking at the same world. Furthermore, the changes in which these discoveries were implicated were all destructive as well as constructive. Scientists are able to account for a wider range of natural phenomena or to account with greater precision for some of those previously known. Later scientific theories are better than earlier ones for solving puzzles in the often quite different environments to which they are applied. That's not a relativist's position, and it displays the sense in which I am a convinced believer in scientific progress." End quote. Perhaps Kuhn should have just borrowed the economic concept from Joseph Schumpeter and simply stated that the principle of creative destruction is at work in the history of science too. After all, the facts, the theories, the concepts of modern science aren't really what's important. It's the process, the methods of modern science that matter. And as messy as our accumulation of objective knowledge about the world may be, modern scientific methods ensure that we are capable of tacking ever closer to truth. Next time on Context, we're going to shift gears away from the history of science to discover other historical forces in other places and cultures that have contributed significantly to humanity's progress. We're going to refresh our historical gaze and focus on one of the most important figures in history covered in Jack Weatherford's best-selling book, Genghis Khan and the Making of the Modern World. I'm Brad Harris. So long.